Hello everyone and welcome back to the channel. So this is where we ended off last time where we were talking about half-life problems and all of that. So just a couple of concepts are now left, but they are very important. So first off, applications of radioactivity. So one of the applications of radioactivity is in household smoke alarms. So it contains americium-241. You don't really need to know the name of this. It's just for general knowledge. But basically this is a pure alpha particle emitter. So basically when decay happens, it's possible that you can emit alpha, beta, gamma, all of these, or maybe like alpha, beta, or alpha, gamma, or any of those combinations. But this one emits just alpha particles. So what happens is that this is your radiation source and this is some circuit. And from here, because alpha we know is a very ionizing source, it creates ions, and as those ions reach the circuit, this causes the flow of current in the circuit. Now when smoke comes here, this basically obstructs the alpha radiation because we know it has a really small range in air as well. So then this obstructs the alpha particles, stops the ions from reaching the alarm circuit, and this triggers the alarm. Now regarding applications, what's asked a lot of the times is basically depending on the different properties that use. For example, in here we are using the ionizing ability. So the examiner could ask something like this, that which radiation should be used here. Now we've already talked about this, so we know that it would be alpha because we want it to be very ionizing for it to create these ions which participate in the flow of the current. Another question which could sometimes be asked is, for example, based off the penetration abilities, which one would be used? Or another thing which is often assessed is how should the half-life of this particle, of this radioactive source be? Now, for example, we're using this in a household smoke alarm. So do we or do we not want this source to run out? Now, for example, in smoke alarms, I really do not want this to run out because that would mean that I replace my smoke alarms really often, and that just increases the cost for me. So I would want it to have a really long half-life so that I can maximize the usefulness of the appliance and use it for a very long time. Another one is sterilizing equipment, and also in this way irradiating food to basically improve its shelf life. So by killing bacteria, we extend the shelf life of such food without making the food radioactive. So for this, we again, if you are asked this question, that which source of radiation would we use so that it just goes through the food and is not retained in the food, so then that should be something which has a high penetrating power. So for that, we should use gamma, right? So it should be very penetrating so that it doesn't remain in the food. And a similar idea is also used for sterilizing equipment. Also killing cancerous cells. So we've done this in the EM spec videos as well. So cobalt 60, just like americium 241 was a alpha emitter, cobalt 60 is a gamma emitter. So these destroy the DNA of cancer cells and prevent them from multiplying and spreading. Point number 4 is in tracers in PET scans. So what happens is that some material, some radioactive source is introduced into the body. This emits gamma rays, and again, now you must be able to correlate your knowledge from before with why we are using gamma rays here. Because we want this to be detected outside the body, we want it to be penetrating so that it can basically escape our skin and our flesh and be detected outside by some machine. Because alpha we know would not be able to make it, and beta as well, if it's stopped by a few centimeters of aluminum, it would not also be able to make it. So that's why we use gamma, and these are used to basically look for cancers or diseases or tumors in certain parts of the body. Again, for this, because you want this to actually go away really soon, so this should have a short half-life, for example, like a few hours, and it should emit gamma because gamma is highly penetrating. Next, controlling the thickness of materials. So this is what the diagram for that looks like. We have some source on one end. Here it's labeled as an alpha source, but it could really be anything. And this is some material which is stretched out between, what do you call it? Between these rollers. So I have my source on one end, I have the GM tube connected to the counter at the other end. And what I'll basically be using with this is, for example, the idea that I know that beta would be blocked by a few centimeters of aluminium, right? So for example, if I had a beta source here, I can control the thickness by seeing how much radiation I am getting here, and by calibrating this, so by seeing that, for example, at a certain thickness, how much radiation am I getting, I can reach a desired value for the thickness for my material. That's the idea of this one. Another one is called carbon dating. So what's the idea about carbon dating is basically using some carbon isotopes to find the age of some sample. Again, it's not what you guys are thinking at all. It's just related to carbon. So by comparing the amounts of the stable carbon 12 isotope with the radioactive carbon 14 isotope, you can estimate the age of anything. So basically any living thing is basically made of carbon and oxygen and hydrogen. So because everything has carbon, so there's carbon 12 in it as well as some carbon 14. So by our observation, we know that, for example, relative to some carbon 12 amount, how much carbon 14 should be there. By the way, carbon 14 is very less as compared to the carbon 12. So if I know how much I am expecting versus the amount of carbon 14 that I actually have, I can estimate how much decay has happened, and that, using our half-life calculations that we did in the last video, we can estimate the age of something. Now this example is inspired from a past paper question. So the half-life of carbon 14 is 5700 years. How old is a bone that only has 1/4 of the natural proportion of carbon 14? Again, I don't know the initial number. Let's say this is some number of nuclei n. So then it becomes n by 2 after one half-life, and then it becomes n by 4. So it becomes 1/4 of what it was. So this is 2 half-lives corresponding to 2 arrows. So this is the value of 1 half-life times 2. So this would turn out to be 11,400 years. So this is the idea of carbon dating. It's pretty straightforward. On to the remaining nuclear processes. So nuclear fusion is the idea that you have two lighter unstable nuclei fusing together to attain stability by producing a heavier nucleus. All right. So fusion basically means coming together, just like how you have fusion cuisine. So that's at the intersection of multiple cuisines. So that's also shown here. You have a helium-2, which is called deuterium in chemistry, isotope, fusing with a tritium isotope H3, giving us helium and 1 neutron and a lot of energy. So again, we can use the conservation of proton and nucleon numbers to see what helium would be. So 2 plus 3 is 5 equals to this x plus 1. So I can figure out that x must be 4. Similarly here, 1 plus 1, and there is no other proton number here, so I know this must be 2. This is very straightforward because a lot of you know the nuclide notation for a helium atom anyway. Alright, so how is energy released here? Again, this is IGCSE stuff, which is that the mass of the products is somewhat less than the mass of the reactants. So this mass which has defected, which has basically disappeared, is converted into energy according to this equation that you might have seen, for example, on the cover of a specific O-level physics book. For nuclear fusion, very high temperature is needed because both of these are nuclei. Both of these are positively charged. And we've studied in static electricity that like charges repel. So when you give them a high enough temperature, which is basically kinetic energy, they can overcome their forces of electric repulsion. Next, this reaction is not really feasible in power stations. So in power stations, the idea is that we cannot really provide a high enough temperature for us to overcome the electric repulsion. So it's not really feasible. But this is what does happen in stars, and because stars do have that high temperature available, and that can bring together the nuclei. Okay, now that somebody has answered the door, we can go on with this. So that's the idea of nuclear fusion. Nuclear fission, what's the idea of this? So upon bombardment by a neutron, a large unstable nucleus breaks down into multiple more stable nuclei, right? So if you have a heavy unstable nucleus, when it's hit by a neutron, it basically splits down into more stable nuclei. So for example, this is the most common example of nuclear fission that is also used in power plants. So you see that you have uranium-235, it's hit by a neutron, gives you barium, krypton, 3 neutrons, and a lot of energy. Again, the nuclide notation of barium we can basically complete using the conservation of the, what do you call it, proton and nucleon numbers. So 235 plus 1, 236 equals to this plus 3 times this, right? So 236 equals to this plus 89 plus 3. So 236 minus 89 minus 3, this is 144 as the nucleon number for baryon, and 92 minus 36, because the neutron has no proton number, that's 56. So you can see that each fission requires 1 neutron, but in place it gives rise to 3 more neutrons. Now this can lead to what is called a chain reaction, where every neutron involved could give rise to 3 more fission events, because 1 neutron leads to 3 neutrons. Each of these 3 can lead to 3 further fission events. So it's kind of like the tree diagrams that you have in math for probability. So you'll have like 1 neutron here, each of these gives rise to neutron, neutron, neutron. Each of these can give rise to 3 more in itself. So what happens is that this reaction, this process can channel out of control very fast, which is also, if for example, if you've seen this movie Oppenheimer, that's what's also being discussed in this conversation between Einstein and Oppenheimer when they talk about the chain reaction. So this is the idea. So how can you control the neutrons somehow? Well, that's exactly what we try to do in modern power stations, in modern nuclear power stations. This is the diagram for that. You don't really need to know this by heart, but you do need to know how each of those components work. So we did this way back in Work Energy Power, that energy released from the fission process is used to boil water into steam, and that drives a turbine inside the generator, which gives rise to electrical energy. So you have a concrete shield here, which basically protects workers from harmful radiations and excess neutrons, because that are also injurious to normal human beings. And then for efficiency, these fragments, which are basically those products of the fission reaction, for example, like barium and krypton, they must be regularly removed for efficiency. All right, so how do we control the rate at which the fission events are happening? So one of these is through the use of control on or boron rods, which are shown here. So these control or boron rods, what they do is that they absorb excess neutrons, and this basically preventing them from participating in fission events. Right, so that's one way that you can have some control over how fast fission is happening. Next, you have the action of the coolant and the moderator together. So this graphite core is basically your moderator, and through this coolant is pumped, which is liquid carbon dioxide, and that also basically absorbs some energy from the neutrons. It slows them down and prevents them from taking part in more fission events. Let's write down how this works now. So for the coolant, carbon dioxide is pumped through the moderator, slowing down the fission neutrons. So again, this is another mechanism by which we can control the rate at which fission is happening. And the moderator, this is just that graphite core through which coolant is pumped. So that's basically all regarding this nuclear power production. Remember, it's fission which is used in the production of nuclear power and not fusion. So that basically wraps up the entire unit of nuclear physics. You've done in a lot of detail what is basically going to be assessed and a lot of ways that it can be assessed. So now watch the videos properly and go on to some topical past paper questions to see how much you've improved with this chapter. So thank you for your time. Like, don't keep this a secret, share it with your friends and subscribe. Let me know down in the comments if there are any other videos that you'd like to see. Until next time, bye.